Alrighty then. Today we're talking about Zero. Zero has so the weird thing is that these days we almost always teach zero as a number first, because most children find that easier to understand. But historically, zero was not considered a number at all. So if anything, if either of these things, it was only used as a placeholder. So it's got me in a little bit of a conundrum because the historical development does not match the typical learning style, at least in Western public schools. And I limit it to my opinions mostly to the United States school system because that's the one that I know the best. I don't actually know a whole lot about other countries' school systems. I've done a fair bit of traveling, but it was all after I was an adult. I didn't really travel much at all until I was 19 or 20 at the earliest. I think, generally speaking, I've decided that I'm gonna try not to get too deep into the history of any of this stuff in this series at least, right? Because most of the viewers for this series are going to be people either trying to figure out what they missed or parents trying to help their kids. Um, I've pointed this out before, and I'll point it out again. This series is not really intended for children, especially not young children. This is more fundamental topics from an adult point of view. I think it's probably too complicated for a typical, you know, 3-year-old or a typical 10-year-old, or I don't know. I think even your average teenager would struggle a little bit with some of this. On the other hand, it definitely be useful to keep it at a level where, a 14 or a 15-year-old could understand it if they really wanted to. At that point, it's not a matter of understanding the topics. I'm not sure that a typical 14-year-old cares enough. Yeah, I do seem to recall a marked increase in the quality of math classes once I got beyond the classes that were mandatory. And the classes that were required classes, you'd always have students who didn't really want to be there. kind of understand why the school can't just let a student leave. I mean, these days, as much as anything else, that's an insurance problem. Because in most places in the United States, at least, once a student arrives at their school, they're on the school's insurance until the end of the day, or in some places until they leave. Some places, a student can leave when they're done with their classes, but they can't leave in the middle of the day and come back for later in the day from other classes. It's kind of how workers' compensation works in the United States, too. Workers' compensation covers you on the way to work and on the way home from work and while you're at work. But if you leave work on your lunch break, that's not covered. At least not under most policies. And for anybody listening who lives in a country that doesn't have to deal with private health insurance and often multiple overlapping different kinds of insurance, you have no idea what I'm talking about. And hopefully you never have to know what. It's not a good system. It too often leaves people who are in trouble in a position where they need to fight with the people who are supposed to be taking care of them instead of being taken care of. Especially when you have overlapping coverages, uh, then the insurance companies will fight amongst themselves to try and offload as much of their liability as they can. And you'll sometimes end up with no coverage and still injured while you're in court. You can have 3, 4, who knows how many interested parties in a court case. It can take years in the worst case scenario. So yeah, if you're ever injured in the United States, you need to get a personal injury lawyer. That's mostly for large injuries, and particularly for injuries where it's not because you did something stupid. Right? If you intentionally did something that was very risky, probably none of your insurance coverage is going to cover you. That's a very negative and depressing topic, so let's choose something else, like 0. What do we want to say about 0 as a number? I think that's probably the more important one here because I haven't actually written those pages yet, but I'm pretty sure I'm going to cover 0 as a placeholder. Covered Because when we're talking about bases, we're mostly thinking about in any numeral system that has a fixed number of digits, at some point you need to roll over, right? And when you roll over, you need to have a placeholder in the position that you just emptied out. So like when you go from 9 to 10, right, the ones position, if you add one more, now you're at 10. The ones position goes back down to 0, and the tens position goes up by 1. Or if you're in a base 20 system, when you go from the 19 digit to the 20 digit, or same for base 8, when you go from the 7 digit to 8. I say the 20 digit, there's no 20 digit in a base 20 system, and there's no 8 digit in a base 8 system, right? That's the whole point, is that it rolls over to the digit in the next position, right? But then you need to set the ones position to something else. You need a placeholder there. I mean, strictly speaking, you don't need to. The Babylonians didn't. They just assumed people would figure out what the what the least significant digit was representing, but saves paper, but it's a little bit unintuitive to somebody who's raised in a modern constant base numerical system. But even now, there's plenty of people who are not totally convinced that 0 is a number. And the reasoning is pretty much the same as societies that historically didn't consider 0 its own number. Is if your main point of view starts from counting, 0 doesn't really make sense. You rarely count from 0. Although there's a good argument here that we should count from 0 when we practice counting, especially with very young children. Research seems to show that though it's not quite the same as understanding 0 as an abstract concept, children as young as 1 can tell when something is missing. So if there's something they expect to be there and it's not, right? They have that kind of understanding. Usually between 1 and 2 is when you can start with basic counting. And during that time frame, a typical child is able to begin to understand the concept of nothingness from the other direction. For instance, when you're eating dinner, a typical 2-year-old can tell when they've finished their food, right? They understand the concept of there is no food left. Right? If they started with some food and then they ate it, they can understand no food. And then when you have slightly older children, probably in the, 2 to 5-year-old range, they can start to understand at a more abstract level. It's probably easiest to start teaching the abstract concept of zero as, I mean, the system that makes the most sense to me is teaching about differences. So here, for instance, we're going from, right, we have the something missing goes to running out something goes to, probably the next step is differences between two things. We understand more and less later the same. Right, and then those concepts extract into this thing equals. So I would that's really where we start to run into equals. If you're doing a completely abstract, built up from nothing construction of a number system, right? You have, usually you start with 0 first, and then you define equals as the difference of 0. Seems kind of backwards. But you can't actually have greater than, less than, or equals until you have the concept of cardinality. And cardinality is quantity, right? How many of something there are. Right? And this is all jumbled together in elementary school, right? We don't, we kind of teach addition and equality in the same lesson. But generally speaking, in a formal derivation, addition needs to come first, right? Because otherwise your definition of equals comes down to numbers equal themselves, which is a rule that pretty much every number system has, or at least all of the most useful ones. You could, in theory, create a number system that doesn't have that rule. I have a little trouble envisioning what it would look like. Mm-hmm. Right, but in this series, I actually think I'm leaning towards putting comparison before the other topics. Right, but now that I say this, and I haven't gotten to comparison yet, but it should at least go after. Yeah, it at least has to go after incrementing, or we'll run into the same problem that I just talked about. Until you get to incrementing, you don't have anything to compare. Right. And I am trying to mostly follow the formal derivation of number systems, because I think that's where we lose a lot of students, is they don't understand why we're teaching them the things we're teaching them. Right? We've trimmed it down to the bare minimum skills that a typical person is going to need by the time they graduate from, elementary school, middle school, high school. But when we do that, we cut out all of the context, right? So it's not clear to those students why the things that we picked are the important things. I kind of do think it would be useful in a lot of places to add, an extra half hour to the school day if it meant covering some of the contextual math and science stuff. Because the history is important, and the formal derivations are important, and alternative systems, I think, would do a lot to help our students understand not just the what, but the how and the why of what we're teaching them in math class. Not it's not super clear to a second grader why they need to memorize the addition tables. And personally, I think subtraction tables make a whole lot more sense if you start to include the idea of negative numbers at the same time, which is why I'm putting negatives right after subtraction. Yeah, I'm definitely going to move comparison down, but do I put it after incrementing? It's definitely after incrementing. But does it go after addition? You could even go so far as to say that it's after subtraction. But I think the concepts in incrementing or the concepts in comparison are too important to say for that long. I think I'm going to put it after incrementing. And if you are wondering why I skip numbers between my titles, that's why. So that I can move things around easily. These 0, 1, 2, and 3, those are pretty well locked in. I can't think of anything that would cause them to move around at this point. There's a possibility that bases could get moved to after 0, but I really don't think so. Right, because with bases, so the core concept of how to actually use a constant-based numerical system doesn't really make sense until you hit multiplication or exponentiation, right? Because we say each column is 10 of the previous column. Right, but for a typical elementary school student, what we're actually teaching them is add a 0. Move over one column and add a 0 to the right. Add a 0 to the right. Add a 0 to the right. We don't typically talk about the meaning of the base 10 system until later on. And I think that's a lost opportunity. I think we should try and at least get the concept down. I'm just not exactly sure how we would teach that. Right? Because to a child that's still learning counting, basically, right? It's hard to explain that the difference, like, not the difference is not subtraction, right? It's the relationship between the columns is multiplication if you don't really understand multiplication yet. Thinking back, first grade was a long time ago for me, but I remember most of our workbooks had illustrations that used dimensionality to describe that topic. Right? They would have individual counting blocks for ones, and then they were probably injection molding plastic rather than being glued together, but they would have blocks that were 10. Like they were sets of 10. They looked like the individual counting blocks, but they were fused together. And then for hundreds, you would get a 10 by 10 square. And again, they were a single piece. They had indentations on them to make them look like they were 100 individual blocks glued together. And I don't know if anybody ever physically made a 1,000 block version of that. Right? They would go out into 3 dimensions for the 10 by 10 by 10 cube, which would have 1,000 blocks if you did that. Right? The dimensionality comparison kind of breaks down there because you can't go 4-dimensional. Right? Even people with advanced mathematics degrees can't really visualize 4 dimensions. Right? We have a lot of side note, the 4-dimensional orthogonal extension is called the tesseract or the hypercube. And we have a lot of tools to kind of represent that, but it doesn't really work on an intuitive level. Because our brains are only meant for 3 dimensions, plus, you know, 3 physical dimensions, and then a bunch of other things that are kind of dimensions, right? We consider time a dimension, but really we only perceive time in one direction. Setting aside the philosophical debate over whether we actually perceive time at all. If anybody ever wants to hear that one, leave a comment. Fair warning, most people respond to that argument either by shutting their brain off halfway through or having a profound existential crisis. Yeah. Because if you follow that line of argument too far, you end up with the conclusion that you can't really prove whether or not you exist. At least whether or not you exist as a being that is moving forward through time. That's actually not provable. Yeah. But that would have to be its own thing, because it's kind of at the border of logic and philosophy. Maybe I'll make a note of that. I don't know. That'll be a much higher number, though. And as I finish these different sections, I'll move them into their own folders. Not that anybody's really tracking my work. I'll try to remember to keep putting the links to the slides in the videos, though, because I do have them set for open for public comment, and that'll last right up until people start abusing that privilege. Because I have the same problem that many teachers have. When you're teaching a subject, it's very difficult to teach it in a way that doesn't assume some level of base knowledge from the student. Right? Or in other words, when we explain something, we explain it from the point of view of somebody who already understands. We forget what we don't know. So it's important to get feedback from somebody who's simultaneously serious about the topic, but also not particularly well informed about the topic. And I don't have anybody who can do that for me right now. Most of my friends and work colleagues are quite good at mathematics. That's a that's a side effect of most of them being software engineers. Hey, they understand mathematics pretty well. A good handful of them have degrees in mathematics as well, so they've they've covered these topics, you know, there and back again. I don't know. Maybe I should make that one relatively soon. That sounds it's a shocking enough topic that maybe maybe it would draw views. Yeah, that's a that's a thumbnail that might draw clicks. You have a title slide. Do you exist? Can you prove it? Yeah. It's a kind of a dangerous video though. Like I said, usually I either have an audience who wants to stop partway through because they're getting uncomfortable, or needs some time to reconcile their views of the universe afterwards. And I'd say that about half the people who really think about it seriously intentionally decide they're gonna discard the conversation. They're gonna ignore the logical outcomes on the grounds that the the logical result does not make them happy, which is totally fair. There really is a point when I think you have to choose whether or not you're going to let something bother you. Even if it's true, there are going to be things that you can't do anything about, and if it's something you can't do anything about, ignoring it may make you happier than confronting it. And that is one of the interesting things that comes out of this particular train of logical thought, is that ignoring the things that makes you unhappy is just as valid an approach as confronting the things that make you unhappy. Again, in most cases with the caveat that it's something you can't really do anything about. Also assuming that your end goal is to be happy. I mean, I feel like that's what many people are going for, but I've certainly met people who, if you went solely by their actions, seemed as if they were trying really hard to be miserable. I also don't understand books like that. And I further don't understand why educators pick books like that to make grade school students read. Like, what was it? Great Expectations by, I think, Dickens? Yeah, Great Expectations, written by Charles Dickens. But I've always wanted to add a subtitle to that book, something along the lines of everybody works as hard as they can to be as miserable as possible. Right? Like, it's a, it's a very famous book. And from a technical perspective, I suppose it's well written and a classic. But man, man, were there a lot of people in that book trying to be unhappy. Like they knew going in that that their actions would make them unhappy. They did it anyway. So many of those characters would have been better off just walking away. I mean, I guess several of them did end up doing that, but or see another one they make us read, Romeo and Juliet. I mean, I get that it's supposed to be an allegory for, you know, how young people not thinking ahead, causes pain and suffering. But I don't like that's another story. I don't think anybody in that entire story made a single good decision. It's also a story about how poor communication messes up basically every plan ever. I mean, these days we usually play the poor communication thing for laughs. We It's a common staple of the situational comedy genre. So you'll have a bunch of people running around not talking to each other and getting into various hijinks. It's also why modern horror movies almost always have to take place somewhere where cell phones don't work. Because how many horror movies from the 70s and 80s and in the 90s don't work if you give all the characters cell phones? Romeo and Juliet certainly doesn't work that way. Just think if instead of sneaking out of the house and calling up to Towers, what if they could just like have a Skype call? You know, go Zoom or Google Meet or Microsoft Teams or all the different all the different video conferencing programs and applications we have today. See, Apple does FaceTime. Facebook has one, but they keep changing what it's called. So much easier to talk to your secret girlfriend or boyfriend without needing to, sneak into the grounds of their chateau, calling up to the window of their tower, and getting chased off at sword point by their cousin. Funny how rarely that happens any day anymore. Uh, is that the true death of romanticism? Is it cell phones? Is that what's done it? Is that why we don't park the car and go up to the door and knock, say hello to their family anymore? Is it really all cell phones that's done this? Right? We don't work on our calligraphy because we don't send letters, only emails. And why sing a song yourself when every song recorded in the past 70 years is available at the touch of a button? I guess digitization. I don't know. If you're from the 80s, though, maybe you think that's the height of romance is making a mixtape for your significant other, finding all the songs that describe your feelings for them and putting them onto, one album, collect all the tracks together, make it into a playlist, share it with them on share it with them on YouTube. I don't know. I wonder if that's still a thing. I I didn't participate in that trend at any age or in any decade. Now that I'm not in now that I'm not in school anymore, I don't get information on the current trends secondhand like I used to. It certainly does tickle my funny bone though to imagine some 10-year-old making a YouTube playlist of love songs that describe their feelings for their significant other. Yeah, I do think subtraction is one of the easiest ways to understand zero. Right. So when the difference is zero, that means the two numbers are the same. That's where that goes in a formal construction of a normal of a typical number system is you usually divide or you usually define incrementing. You go from 0 to 1 to 2 to 3, right? You define how you always get to the next number in your system first, and then you usually define addition as repetition of incrementing. Right? So to say 2 plus 2 is the same as saying 2 plus 1 plus 1, right? So incrementing is adding in the whole numbers and the integers. It it kind of doesn't have to be plus 1, but generally speaking, the number 1 is defined together with the concept of the increment, right? The operation to increment, right? You would typically explain it as adding 1, but if you're trying to define it, you would go the other way. You would define the increment operation, and you would say the difference between where you started and where you ended on an increment operation is the definition of the number 1, right? That's that's one of the things that you need to define when you're creating a number system. You define what it means to be 1. You start out with defining 0, and then you define what it means to be 1. And the operation that takes you from 0 to 1 is the increment, right? So 1 and the increment operation kind of get defined together. So in that sense, 1 is actually a little bit less fundamental than 0 is, which solidifies my decision to put 0 before incrementing, right? And then counting is what happens when you increment and pause, then increment, then pause, then increment, then pause. Right? Right? And then addition is when you increment a whole bunch of times at once. And then multiplication is when you add a whole bunch of times at once. Exponentiation is when you multiply all at once. Then after that, we give up creating new names and symbols for it. We just start adding arrows. And you'll notice that sometimes exponentiation is symbolized with either a caret or an up arrow. Right? But then if I put 2 up arrows, then that means I'm doing exponentiation multiple times. If I put 3 up arrows, that means I'm doing the 2 up arrow operation multiple times. If I put 4 arrows, I'm doing the 3 arrow notation. Right? Actually, calculating numbers using arrow notation is not that useful because it results in extremely large numbers very quickly. Usually you would only use that sort of notation when you're trying to prove when you're trying to prove that something exists, right? If you have a question that says, does such a number exist such that it has this list of properties, right? Oftentimes, finding a number that satisfies the list of properties is too difficult. So what you end up doing is you construct a number that has those properties. Like this is a overly simple comparison. Or, well, it's not a comparison. It's an example. It's a fair example. It's just a little bit simple, right? If I wanted to know a number that had that was a multiple of 6 and 10 and 100, right? I could multiply 6 times 10 times 100, right? Is 6,000. 6,000 is definitely divisible by 6 and 10 and 1,000. It's by no means the smallest number that's divisible by all of those, but it definitely is one. So if you don't care about how large the number gets, right, you can find, I mean, given any finite set of numbers, you can find a number that is divisible by all of them just by multiplying them together. It's easy. It just your result is probably going to be quite large. And sometimes if you're working with a computer, you might just do it that way. Um, there will be some size of number after which a computer becomes less efficient. That number is a great deal larger than the number at which a typical human becomes less efficient. But you don't really need to you don't really need to simplify on the computer until you reach that point. You know? Sometimes we don't even care what the answer is. So we'll take the numbers that we start out with and we'll create operations that lose information. Things that you can do to the numbers quickly, but that don't carry enough information to figure out what the resulting number is. So we'll do something saying, if we're looking for a number that has properties A, B, and C, we'll maybe start out with what kinds of numbers have properties A and what kind of properties have B or C, right? And then we'll think together, what would it take to combine numbers in column A and numbers in column B and numbers in column C to give a result that has all of those properties. And if we've proven that those numbers do exist and that there is an operation to combine them, then we're done, even if we haven't calculated a single example number that has all three properties. We've proven that the number does exist, we just don't know what it is. I'm not sure that that's something everybody's comfortable with. If you want to pursue a career in theoretical mathematics, like number theory, that may be something you want to square yourself to. You want to you want to align your expectations because we have a fair few results where we know that the answer does exist, We just don't know what it is. Often just because the first example is too large. Right? We have plenty of questions where we know the answer exists, but a way to calculate the answer is not obvious. And simply trying every number only gets you so far. There are definitely people out there doing that, though. They have computers just running, saying, here's, here's a way to generate numbers that could have the properties I want. And they just have one computer generating possible numbers, and then they have another program. They have another program just checking to see if the number has the properties. And they just have it set up so that if it ever finds one, it'll send them an email and tell them, hey, I found a number with those properties you were looking for. But even the fastest computers can only check so many numbers a second or an hour or a day. Yeah, I think understanding zero through addition is kind of underwhelming. Unless you're willing to introduce negative numbers. I think we usually put negative numbers after subtraction, right? Because what we're really talking about when we introduce negatives, we're talking about upgrading to the integers. Right? When before then, we had been working just with counting and incrementing, right? That gives us whole numbers, and natural numbers. Depending on whether or not you include zero. So Yes, and nobody agrees. In fact, it looks like some people use whole numbers to mean the integers. That one's not common. At least where I went to school in New Jersey, you normally use natural numbers to refer to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and whole numbers to mean 1, 2, 3, 4, 5, 6, 7, 8, 9. I really feel like as a kid in elementary school, I was taught the opposite, that whole numbers started at 0 and natural numbers started at 1. So the answer is going to be whenever you're talking about whole numbers and natural numbers that you confirm with the people you're talking to which set you're actually talking about first. Especially if you're going to use whole to mean integer, you should definitely bring that up, because I feel like whole numbers is more commonly used to mean either 0 and up counting by 1 or 1 and up counting by 1. I think it's probably too late to standardize it though. Too many people using the words too differently. Like if like what kind of standards organization would would even promulgate that? The International Standards Organization, maybe, right? Like if you tried to get like the United States National Institute of Standards to do it, they'd probably just tell you no, because even if we standardized it in the United States, it wouldn't fix the problem. Because people in other countries are not in a big hurry to use United States standard systems. It's very strange. It's almost as if we were one of the last countries still using the imperial standards instead of the metric standards. For the record, the imperial standards is a bit of a mishmash, but most parts of it are either base 2, base 3, or base 12. Not totally sure where the base 3 parts came from. Right. Like 3 teaspoons in a tablespoon, or what is it? 3 grains to an inch? 3, like the original one was 3 barley corn, maybe, became the basic unit of length. Which is probably better than making the foot definitional, because foot sizes vary. Not that barley corn sizes don't vary, but I guess at least if you got a whole bunch and mixed them up and then laid out 3, not just once but 4 or 5 times, you could get a decent average. Right up until somebody starts breeding barley corns for their length. messes up all your calculations. Yeah. So there definitely is something to be said for having whatever your base unit in each of each type is be something that can't change. Right? Like the basic unit of charge is the charge of an electron and or proton. Electrons are easier to measure than protons usually, but they have the same charge. Right? We just call that charge 1. Right? That's why a proton has 1 charge and an electron has -1 charge. That's we haven't found anything ever that has a smaller charge than that. So as far as we can tell, that is the smallest difference in charge you can have. And we have this thing called the watt balance. It's basically like a really fancy scale. And we can use that to precisely measure weight using electricity. But it uses not just the voltage. Voltage is a unit of charge. It also uses the amperage. And I think amperage requires time to construct. I think amperage is made out of amperage is a measure of current. If I recall correctly. Oh, that's interesting. I did not remember that quite correctly. The International System of Quantities uses current as its base quantity, not charge. Uh, does the system even address charge? Because they have length, mass, time, current, temperature. They have amount, just like counting, and luminosity, luminous intensity. I don't know that those would have been the 7 that I picked. Yeah, this comes down to the whole debate of at some point you just, at least one quantity you have to pick and set it to 1. So there's an argument for setting the speed of light. Seems to, that, as far as we can tell, that's a physical constant. Mass doesn't seem to, right? Mass doesn't really seem to have any really obvious constant value, I guess. Right. Subatomic particles generally have a fixed mass. Depending on your relativistic frame of reference. And there's caveats to everything within physics that depends on your frame of reference. Right? But different particles all weigh different amounts, so there doesn't seem to be a definitive smallest particle. Quarks are pretty darn small, but I don't know that. I don't know that they're really. Length. The jury is still out. We're not really sure if there's a smallest fundamental unit of length. There's a unit of length below which all of our current equations stop making sense. Right? That's the Planck length. Right? You can do some calculations that give you answers like the radius at which the vacuum energy of the universe causes a black hole to form. As far as we can tell, the vacuum energy is the lowest energy that can exist. Or rather, might be more precise to say the lowest energy density that can exist. Right, but if you look at it as an energy density, then that sets a minimum size below which our equations for black holes say black holes should form. And if you follow that idea up, then everything should be made of black holes. Or maybe not. The answer is we don't actually know. Both ideas could be wrong for all we know. Time, so far as I know, is completely arbitrary. I know of no way to subdivide time in any way that doesn't seem continuous, all the way down to 0. Right? You could take the Planck length and the speed of light, and you could calculate a Planck time, quote unquote. That would be the amount of time that photon takes to move one Planck length. Unknown whether or not that has any real physical meaning. Maybe we just don't know. temperature has a fixed 0, but not, so far as I know, a fixed interval or increment. Right? This is why I think the centigrade versus Fahrenheit debate is kind of silly, because neither of those are even a good option, because they both of their 0 points are wrong. Right? You say, well, centigrade is based on the freezing point of water, and my response is, so what? Why is water special? And why is the freezing point valuable? Sure, those numbers are useful, more or less. But, you know, if you wanted to base your system on something that was as fundamentally correct, like based on physical constants as you can, you would put your 0 at absolute 0. So the International System of Quantities uses Kelvin, which sets 0 to absolute 0 and then uses the centigrade degree as its increment. There is an analogous system known as Rankine, which sets absolute 0 at 0 and uses the Fahrenheit increment as its increment. I guess probably the reason people don't like Kelvin. This is the fanatics who want the freezing and boiling of water to be their set points. It's because if you make the space between freezing and boiling of water 100 degrees, as in Celsius or centigrade, then you get 273.15 something Kelvin. It's right. So you could either have a perfect 100 between freezing and boiling, or you could have the perfect round number for freezing and boiling. But not both if you put 0 at absolute 0. Yeah. I don't know which one people would hate less. Now I kind of want to write up the system where let's see, what would that be if we just on my monitor somehow. One of these USB ports has to be bad. I'm gonna put a cable tie or twist tie or something around that to mark this cable and remind me to replace it. Yep, I have some USB. Let's see if we have some. But if I wanted in my new system, which I'll call A because nobody's using A for temperature. 100A. So that would mean that 1K so in this case, I'm talking about a difference of 1 Kelvin is the same as 1 Celsius because they use the same. Okay. So that would equal 12.73-ish. Right, which would mean that 100C would equal 100 plus 200. Right, so you could make a system where absolute zero was zero, and then water freezes at 100. Did that backwards. One over. That'd be makes more sense. And I knew I had done that wrong because I know this space between absolute zero and water freezing is significantly larger than this space. Right, so this is no longer to scale. It should be there. I don't think anybody would like a system like this any better. And we could make this 200, 274. Then. Yeah, I don't know that anybody's going to like that system any better. But that just goes to show sometimes different systems are convenient for different uses. And we maybe just have to accept that. Right? The Fahrenheit people like their system because the range of temperatures from 0 to 100 are useful everyday temperatures. more or less. I think the probably 10 to 30-ish Fahrenheit are not that useful. Right, so the high 20s are the temperature you should keep your freezer at. Low 30s are your refrigerator. And 50 is a light coat up through 100 is uncomfortably hot. Depends on where you live, though. I've certainly met people over the years who considered 60 Fahrenheit to be shorts and t-shirt weather. That's 15C for anybody who doesn't speak Fahrenheit. Got a message that my groceries will be delivered in more than half an hour or less than an hour and a half. Dude, I really want some junk food though. But I'm not going to eat any. I am eating healthy food only for a while. Let's see. I got off track because I think it started somewhere around when I was considering whether or not zero is easy to understand with addition. And then I started moving around the order of things. Mm. And that's useful for understanding why things times zero is zero. I don't think that really, I don't think that really helps understand zero, but it helps understanding multiplication. Yeah, I just have to addition. kind of tricky because those, I think all three of these topics really go together. Or rather, comparison definitely goes after incrementing. Addition definitely goes after incrementing. But really the catch is that you can't. I mean, I had comparison up above, right? Because can you really increment without the notion of equals? Right? You could split equals into its own thing. But equals is one of those concepts that I think people usually get. At least the fundamental concept. There are some. Once you get to algebra, the idea of equations sometimes throws people off a little bit. Maybe I'll actually do equals first, and then I'll include that bit with the equations. Most of the people that this is targeted at will already know what both of those concepts are. Their understanding may lack accuracy. They may not have perfect understanding. On the other hand, I bet you could get the idea of equations across to a kindergartner or a first grader. Right? You had a picture, right? Because we teach them the idea of equals. We show them a picture of 5 apples, and we show them a second picture of 5 apples, and we say, these both have the same number of apples, therefore they are equal. the idea of the equation is really just that if you change the things on both sides the same way, they'll stay equal. Right? So you could add 2 oranges to each side. Right? You say on the left we have 2 oranges, and on the right we have 2 oranges. So those oranges are equal. We combined them so that we had 5 apples and 2 oranges on the left, 5 apples and 2 oranges on the right. See how they're still equal? That's really all equations are. If we traded out all of those fruit for, I don't know, toy cars, then we would have 7 toy cars on the left and 7 toy cars on the right. They would still be equal. Yeah, I think maybe equations do go a lot earlier in the system than we usually teach them. I'm 80% convinced. I'll give myself a think on that. I'll come back to it. And then that would make this would no longer be general comparison. This would be less than. So now that raises the question of, do I want to introduce the concept of ordering here? Right? Because orderings and partial orderings, the only things they require are greater than and less than, possibly equality, depending on whether or not you're allowing repetition in your ordering. Usually when you're ordering things, if things are equal, you say they're the same. Right? You actually bucket them together and treat them as the same thing. Not 2 things with the same value, but the same thing. Except for when you don't. Like at the Olympics, which is going on right now, I think. I haven't really watched any of it this year. Right? You'll say, if you have a tie and those people both get the same rank, but you don't try to argue that they're the same person. On the other hand, you do argue that they get the same medal. So if you're only viewing people by their medals, then you would say, if they tied for silver, then you'd have 1 gold medalist and 2 silver medalists. That's the thing about ordering, even in a practical sense. When you tell like a computer to sort out some values that you've given it, even if they have lots of other values, it only checks the values you tell it to care about. So it may or may not give you, these are called, the values the computer cares about are called key values, by the way. If you give it items that have the same key value, it's going to depend on who wrote the sorting algorithm, whether or not it uses any of the other values to guarantee which order it gives you them in, or whether it gives you some sort of bucket or box or container that has all of the items with the same value in it. That's another strategy sometimes. Hmm. Don't know. Ordinals are tricky. But they're tricky because they're so similar to the cardinals rather than because they're different than something we understand. It's not that people have difficulty really understanding what ordinals are. The tricky part is understanding where a line between the ordinals and the cardinals is. Mhm. That's going to require some research. I don't know how to cover that topic, and where it goes is really going to depend on how it gets covered. Is there anything else really that I want to cover about zero here? Right, because zero is a placeholder is going in. It's going in the video about constant base number systems. Yeah, whether we should start from zero and counting, that's a topic people fight over. How do we make sure? How do we make sure that a listener really understands equality? We haven't introduced subtraction. We haven't introduced addition yet, or even counting or incrementing yet. Which means we can't really go with the technical definition, right? Because the technical definition is all about cardinality, right? I keep talking about the difference between cardinal numbers and ordinal numbers. Right? Cardinal numbers are the counting numbers, and ordinal numbers are the ordering numbers. Right? So if we haven't done counting, then we can't blow equality off as saying they're equal if they have the same cardinality, which is true. I mean, that is how we're going to have to explain it, just without the technical terminology. So do we go with the apples and oranges comparison? That's really probably sufficient, right? Because most of the viewers are going to look at this and go, yeah, I get what equals means. Let's think about this the other way. What's the most likely misconception that a viewer would have about equality? And specifically, we're talking about cardinal equality here, because equality is where, in really advanced math, equality is where ordinality and cardinality really diverge, right? All the basic arithmetic is pretty much the same, right? You're in first place and then you drop 2 places, now you're in third place, right? If you had 1 and gained 2, you now have 3. Works the same. Ordering, ordering inequality. But that doesn't show up until you start dealing with infinity. And broadly speaking, I don't care if anybody who's not a math major understands infinity, like really understands infinity. I'm not super tempted to even cover that other than as interesting side note that there are different sizes of infinity. And that's where ordinals split out separately. The ordinal infinities fall in between the cardinal infinities, if that makes any sense. Probably not, because it doesn't actually make any sense. I could rant about that, but I'm gonna hold myself back because that's way off topic and also really quite confusing. I'm not currently trying to blow your mind. Currently trying to make better progress on my foundation series. Mm-hmm. Hmm. I'm about to put forward an opinion that I feel is correct. I feel it's the most useful standpoint to make. And note that I really am trying to focus on useful things in this series. Hmm. I'm going to propose that two sets are equal as long as all of the important things are the same, right? This goes back to number 2 here, where I propose that the whole point of numbers is comparing things, right? So equality is the first comparison operator. Unless you count being incremented as a comparison operator, and I generally don't. Right? Incrementing is important because it's there for counting, but being one greater than, right? That's why we do. Incrementing is important for counting, and counting is fairly distinct from addition, right? So that's why incrementing and addition I usually treat separately. But being greater than by 1 versus being greater than by some other value is not as distinct in our day-to-day lives. Hmm. Yeah, so I don't think I would typically count having been incremented as a comparison operator because we just don't use it that way, right? If it was 1 greater than, we would still say that it was greater than. Yeah, I think that tracks. And this, I think, is the big difference between two things being equal and two things being the same, right? If you want to say two things are the same, you generally mean they're exactly the same, right? Often we use this in a sense of like it's the same person, right? In which case it's literally one person who is doing one thing and then doing another thing, right? Those two people are equal, like identically. They're literally the same person. Whereas when we say two things are equal, it's usually more nuanced. It has a value attribution that is not really there for the word the same. In fact, that kind of shows itself in the phrase, it's the same difference, which English teachers hate. But as a mathematician, actually, that's a totally valid sentence. It means that the two situations are different by the same amount. Right, so to simplify it just to numbers, 3 minus 1 has a difference of 2, and 4 minus 2 has a difference of 2. So 3 minus 1 and 4 minus 2 have the same difference. But what we usually mean that to mean is all the properties I care about are the same. And it really has to be restricted that way, because otherwise no two things would ever be equal. Right? There's no matter how similar two items, pencils or pens or erasers or whatever, that come off of an you know high-speed factory assembly line, right? They're not exactly the same. Depending on how deep you want to go into philosophy, it's questionable whether two things even can be exactly the same, whether that's even within the realm of possibility. At the very least, any two different things have different positions. Right? You can't have two things in the same place at the same time, as they say. And that's actually true. That's one of the more complicated and yet fundamental aspects of quantum physics is is particles with certain values of a quantity called spin that I'm not getting into here because spin is only roughly analogous to macrophysical spinning. I always forget whether it's the integer number spins that can't overlap or the fractional spins that can't overlap. I think it's the whole number spins, but don't quote me on that. Yeah, certain types of particles can't overlap. Right? And without that, no two physical objects can ever be exactly the same. Right? They'll always have slightly different position or slightly different velocity. And we usually kind of skip over this idea when we're teaching equality because in math, numbers are the same because numbers are completely abstract. They have no physical presence. So every two is exactly equal and exactly the same as every other two. No judgment on whether or not you like apples better than oranges, or vice versa. I had oranges today. Maybe I should get some apples next week. Yeah, unrelated, but I've recently replaced all of my starchy and sugary breakfast foods with fresh fruits, which is almost certainly better for me. And I'm trying to convince myself that it's worth it to live a healthier lifestyle. Which is why I'm craving junk food, because I only started a couple of weeks ago. Which means that any day now, any day now, healthy eating should become the new normal. But I'll stick to my healthy diet until it does feel like it's normal. I'll have I'll have an occasional treat after that, but I want to wait until healthy feels normal, and then treats can be just that. They can be treats, occasional treats. Because if I ate some junk food now, then my brain and my body might try to convince me that junk food was still normal. Why, when I go to the grocery store's website, does it always give me all the things that have apples in them? And it label it. Sigh. And it's listing every variety of apples separately. Also, which apples are the best apples? I don't even know. I know that some of these are grown to look nice instead of tasting good. Which apples taste the best? Language internet, you can't say that on the screen. I don't necessarily think you're wrong. Red delicious apples were potentially delicious once upon a time, but they've been heavily selectively bred to look nice and to ship well without bruising or getting discolored or dented. And somewhere along the line, they didn't taste good anymore. So if they're good, both plain and in pie, that means they're probably a little bit sweet or a little bit sour. Yes. Tart with a little bit of sweetness, as opposed to cameo apples, which are sweet with a little bit of tart. In this case, I don't like apple skin at all, particularly not crisp skin. I think it feels weird to bite into something with a crispy skin. There's a good chance that if I get apples, I will be throwing the whole thing into my blender and turning it into apple cider. I will leave most of the skin and the pulp in because it's good for me, but I don't like chewing on apple skin. It feels weird. Same here, the texture doesn't matter as much to me. Right, and this is what I was saying earlier about things are equal if if the parts you care about are equal. Super sweet. Super sweet is probably too sweet for me. Firm and sweet with a crunchy texture. Let's see. I like Granny Smiths when cooked. Maybe I'll get a couple and I'll bake them and put some cinnamon on them. Yeah, because I think they hold on to a good flavor once they've been cooked. They're really sour to eat by themselves. So it looks like there are 4 of them that are recommended as being juicy. Yes, thank you for coding the screen in advertisements. Apple advertisements. Let's see. So I'm looking to see if my grocery store has Cameos, Empires, Rappensteins, and Honeycrisps. Mm-hmm. Do have some of these. Not sure I want to buy a 4 pound bag. Might be too many. Me to eat by myself. I would likely make myself a little bit sick if I did that. That's probably buy 6 in total. That'll last me all week. Hmm. Looks like my groceries are almost here, so I'm going to sign off and bring those inside. Make myself some dinner. And see you in the next one.